Yes, good evening and welcome. It's great you're here. My name is Stefan Kraus. I'm from the astrophysics group at the University of Exeter. And it's a great pleasure to welcome you here, either in the alumni auditorium at the forum or online, if you join us there. And it's also my great pleasure to welcome our speaker, Dr. Frank Eisenhauer, from the Max Planck Institute for Extraterrestrial Physics at Garching, Germany. Dr. Eisenhauer is also a Privatdozent or adjunct teaching professor at the Technical University of Munich. This lecture today is linked to a conference on high angular resolution astronomy that is taking place at Exeter this week, named The Sharpest Eyes on the Sky. As part of this event, we host about 45 international experts that are visiting us, as well as another 80 experts that join us remotely. And we are discussing scientific studies that achieve the sharpest view of celestial objects, in some cases up to 100 times sharper than what you can do with conventional telescopes, such as a Hubble Space Telescope. And as part of this conference, we discuss results that sometimes appear unbelievable, even subreal to me, such as imaging the nurseries where planets are forming around young stars, seeing surface structures on stars other than the sun, characterizing the atmospheres of distant exoplanets, or resolving the dust tori around distant galactic nuclei. Yet some celestial object that we will hear about in this public talk today stands out because by its very nature, it doesn't emit any light, but is the darkest dark that you can imagine, a black hole. In fact, it's a black hole 1,000,000 times more massive than our sun, sitting at the very center of the Milky Way. Proving the existence of this mysterious object has been a decade-long quest that required not only pushing existing telescopes to the very limit, but also to build new instruments with unique capabilities that enable these extremely challenging observations. And our speaker, Dr. Eisenhauer, has led the development and the scientific exploration of two of those instruments that played a key role in this quest. The instruments developed under his leadership contributed to the discovery and characterization of the galactic center black hole, for which 3 researchers were awarded the 2020 Nobel Prize in Physics. For this leadership role in this technology developments, Dr. Eisenhauer himself has received also many prestigious awards, including the Tycho Brahe Medal of the European Astronomical Society, the Stern-Gerlach Medal of the German Physical Society, and the Jackson-Quilt Medal of the Royal Astronomical Society here in UK. So it's my personal pleasure and privilege to introduce Dr. Frank Eisenhauer. The floor is yours.
Thank you very much, Professor Kraus, dear Stefan, and dear colleagues from the university here at Exeter. It's a real pleasure for me to be here. It's the first time I'm here, and it's a wonderful city and a wonderful university, really a nice place. And well, you have already given the full talk. I don't know what I should talk in addition. I have a pretty strong accent. I'm trying my best. But I hope you get the messages. At least I have nice movies in case you don't get the message verbally. So it will be about the black hole in the center of our Milky Way. And what you see here is our Milky Way. So this is how the full sky would look like if you have a fisheye objective on your camera and you make a deep exposure. Maybe you can dim the light actually a little bit because I will have a number of these dark pictures. And so when you have a very clear sky and you can see the full sky, it will look like that. So you see the normal stars, but then there's a a band here of stars which your eye can't resolve. This is why it looks like a Milky Way. But it also, if you look closely, and this you see by your eye, there are also these dark patches, and then you have a kind of a bulge in the middle. This is the middle of our Milky Way. This is where our Earth, our sun, is rotating. We're out at a distance, something like that, around this center of our galaxy. And so this talk will be about an object which is here, but which you don't see. And the reason why you don't see it here, and so this is a little zoom to this photograph is here, because you are right in this very dark region, and this is foreground extinction. So the universe is not empty, actually. There's a lot of dust, exhaust, so to say, from stars which have exploded, and you can't look through. And so it took a while, actually, to realize that the center of the galaxy is really here, and you can look through this dust if you go to different wavelengths, energies. You can use X-rays, for example, as you know from your doctor, or you can go to the radio, or you can go to infrared wavelengths or heat radiation. In all of these wavelengths, you can look through the dust, and then the galactic center looks very different here, what you have in the very center. You see gas in spirals, in the radio wavelengths. In the X-ray, you see also gas, which is coming from earlier supernova exploding stars. Or if you look in the infrared, and this is what I will concentrate today, you will see many stars, a star cluster in the very center. Still, you don't see a black hole. It just looks like a massive cluster of stars. So it took a while after infrared detectors were developed, then to also make sharper images. And to make sharper images, I will talk about it. This is called a technique called adaptive optics, where you remove the blur from the Earth atmosphere. Then you can actually see the central part of the galaxy very sharply, individual stars. Then I will talk about you that seeing just stars is not enough. You also want to have velocities, and you can measure velocities, for example, like the police with a radar. This is what we in astronomy would call a spectrum, a Doppler shift. And for that, you make spectroscopy. You look on lines which are emitted by atoms. And then you can bring, actually even better, you can bring the biggest telescopes in the world together and get ever sharper images. This is called interferometry. And finally, you arrive at a black hole in the very center of the galaxy. So this was now a short introduction of the full talk, which I will give. Now let's go a little bit one by one. So let's first introduce what is a black hole. And the concept actually is coming from a time somewhere in between Newton. So Newton was the one who discovered the law of gravity. The more mass you have, the stronger or the faster the apple falls down. And then actually before the big telescopes were developed, there was another very famous British, John Michell, who made the thought experiment: if you make our sun 500 times as big and keep the density, then you can calculate from Newton's law that the velocity of a stone falling down of it will be the speed of light. So light will not be able to escape. You will have a dark star. This is what he named this object, this thought experiment, this Gedankenexperiment. The more modern world of that was coming in the beginning of last century with Albert Einstein. So Albert Einstein was then developing the next theory of gravity. So after Newton, now our current understanding is that the force of gravity is actually carried by the space-time itself. So what you will see is that space is not straight anymore, it's curved, and it's space-time. Also time will go at different speeds depending where you are. And so this is what Einstein introduced. And the surprising thing of this dark star, so if you make an object compact and massive enough, is actually that there will be what we call an event horizon. This is a region where in this picture time stops and the curvature gets very strong of the space-time around. Whether these objects are truly objects which exist or just a mathematical building out of the formula, it was then Penrose who also got the Nobel Prize in 2020 for his theoretical work. And as we will see, and he has proven so nicely, is that if you have such a dark star dense enough and small enough, it will inevitably collapse to an object which has exactly the special things, this event horizon where time stops and where there's a singularity in the middle. We will also come to that, which causes troubles up to date. So now this is a 40-year journey then between these conceptual ideas that these dark objects are black holes. And so you see some of the astronomers who have contributed to the science, and they call it a 40-year journey. So this is a slide from one of the Nobel laureates in 2020, Reinhard Genzel, together with Andrea Ghez, who got it and Penrose for the theoretical work.
Okay. Try to remove this.
There is a way to do it.
Yes. Okay.
And so it's a 40-year journey, which I took from his slides from the Nobel lecture. And we will follow through some of these measurements here. It comes back until we will kind of, I would not call it a proof that black hole exists, but that the sum of all of the arguments and observations make us very, very convinced that a black hole exists. And so now you disabled my screen. But I'll manage like that. So let me come back now from the theoretical side to the observational side. And this goes back to the 60s and 70s, of the last century. And so the first, so to say, discovery that black holes can truly exist was coming from objects like that. So they were in Cambridge, they observed the radio sky. They found a lot of stars which shine in the radio. This was mysterious. A normal star doesn't shine in the radio. So this is one of the stars. And then Martin Schmidt made a spectrum of this object. And they see that this emission from these atomic lines were at a very high velocity, as if the object is moving away from us. And back then, we already knew that the universe is expanding. And you could translate this velocity in a distance. And you will find that the star is 1 billion light years away, but it's still as bright as nearby stars. So what could it be that there's an object 1 billion times away and still so bright? And so you need an energy source. You can calculate it on the back of the envelope, which is more than you could get from a nuclear fusion or a nuclear bomb or a nuclear explosion. And so the only source of gravity was already then, back then, the argument you could have is if you have a black hole, you can let matter fall very close, heat it up, and convert this kinetic energy to light. So this was in the 60s. And then at around the same time, a little bit later, another Nobel laureate, so this is Riccardo Ciccone from the US, they put the first X-ray telescopes on satellites on orbit. And then they found a few point sources, which we now know are neutron stars or stellar black holes, small black holes in our Milky Way. And some of them live in a double stellar, so 2 stars, a black hole, another one. And so they looked with the X-ray telescope Ciccone, and they've seen such an X-ray source which always gets dark for a short time, then it goes behind the other star. But they couldn't see any emission from this object. And so this was the discovery of the stellar black holes, smaller black holes, roughly a few times the mass of our sun. Now we had these elements that in the center of galaxies are very massive black holes. This is what Schmidt has discovered. So what about our own galaxy? In the center of the Milky Way, which you have seen, there was for a long time, there was the argument there is no black hole because we don't see anything. We don't see particular X-ray emission. There's not very strong radio emission. There is not this bright star as Martin Schmidt has seen in this very distant galaxy. So it was yet another Nobel laureate, and so this is Charlie Townes. And he's a remarkable person. He was one of those who invented the laser, that laser, and then switched field to astronomy and really realized the power of infrared astronomy, that you can have access to atomic transition, which you don't see by eye, but at infrared wavelengths. And then so he could look on the motion of this gas, which you see here at radio wavelengths, but can't measure the velocity at the radio. You can do that at infrared wavelengths. And so in the 70s, 80s, now Charlie Townes, he measured the velocity of this gas, and you've seen that this is moving a few hundred kilometers per second, towards you, the other one away. And so he could measure that there must be an object in the center, which is a few million times the mass of the sun. And so it was pretty much only Charlie Townes who was convinced that there's a black hole, despite you don't see anything. And so since then now, it was a quest to actually see this black hole in the center of the galaxy, and I'll take you on a little road trip towards it. So we start from this all sky picture of the night sky. We zoom towards what is the center of our galaxy. You see nothing. This is the dust. You only see stars, which are in the foreground. And then only in the 90s, actually, this was coming a lot of the technology out of the military. We got access as astronomers to infrared detectors, which we then could use, put on our astronomical telescopes and look through the dust and then towards the center of the galaxy. And you see they get ever more stars, ever more compact. And so this is the most massive region of stars in our galaxy. Still, there's no black hole. All of what you see are stars. So could it be that there's really no black hole? And so infrared technology, as I said, it was a fantastic time for astronomy. It was still very experimental, small business de facto. We got access to quite some technology which was coming out of the space defense. And in particular, this infrared detectors and then other things like adaptive optics and imaging spectroscopy, I'll touch in a second, the infrared detectors. And then so you could look into the central part of the galaxy. There's now a small patch, as you would see if you look with a small amateur telescope. And there are hundreds of stars within a very small part. It's really a very tiny part of the sky. So the trick was now to get sharper. But you don't get so easily sharper when you make a big telescope, because there's the Earth atmosphere, there's wind, there's turbulence, and this mess which the turbulence does actually makes the amateur telescope of that size as sharp as a 10-meter telescope. In order to actually then retrieve the sharpness of a big telescope, you have to do tricks. And the first tricks which were applied, and so this Andreas Eckert, which was also joining our institute, back then to actually take these infrared detectors, make very short exposures where you actually freeze the effect of this turbulence. So you see substructure, and then if you run enough computing power, which was also becoming available at the time, you can make sharp images. And these were these two groups. So one around the other Nobel laureate, Andrea Ghez from the University of California, and a group around Reinhard Genzel and Andreas Eckert in Munich, in Garching, next to Munich. And so they could zoom in, and they've seen ever more of stars in the very center. Still no black hole. You would see the stars are moving very fast. This is what they've noticed immediately. So fast that there must be a big mass which swirls them around, but no emission from a black hole either. I'll come to that, why it should emit also a little bit later. But the stars were moving so fast that there must be an object which keeps them. They're moving so fast, if there's nothing to keep them, they would fly away. And so then came this technology beginning of around 2000. Now two things happened and where we've contributed in our research group. So this one is adaptive optics, which is then to correct in real time the Earth perturbation and the turbulence. And the other one, which is to make spectra at the same time as the sharp images. And so let's first start on this adaptive optics. And for that, I have a little animation which illustrates what happens. So you have a big telescope, 10 meters in size roughly. You have a star, and the light which is coming outside in outer space, it's unperturbed. Light is described by a wavefront, but now if you have turbulence, the wavefront gets perturbed with the turbulence of the Earth atmosphere. It's like you look on the highway, when the sun is shining on the highway, you see the flaring around. And what we now do in adaptive optics, we measure the shape of this wavefront 1,000 times per second. Then we put a little mirror with many actuators, 1,000 actuators, and every millisecond tweak the actuators, such that in the end this perturbation is corrected. And you get an image which is as sharp as such a telescope can do. And so it's then what we call diffraction limited. The size of the telescope can tell you how sharp you can do it. The bigger, the better. So this was the adaptive optics. But now I explain you also a main problem of this technology is you have to measure 1,000 times per second. How is the shape of such a wavefront, we call it, of the light, the perturbation. So you need enough photons, enough light to measure that quickly. And stars are too faint, certainly in this region which we want to look in the center of the galaxy. So we have to make our own artificial star to sharpen the image. This is called laser guide star. And so what you do is actually you put a little small telescope on your big telescope, and you shoot up a laser to the atmosphere. And then if you take a special color of this laser, a special wavelength tuned to this yellow light, which you know from the street lights. So this sodium, this is a metal. Actually, you see the light is scattered at the molecules of the atmosphere, then it goes almost in outer space, no scattering. And then up there, there's like a screen where you see a resonance, where you see the laser light absorbed and being re-emitted at this very special wavelengths. This is where the falling stars come down. They bring a little bit of metal in our atmosphere, they evaporate, and up there you have this free metal, which you can use as a screen to shine it back to run our control loops and charm the image. And the other thing is what we need if we want to measure well the motion of the stars. We do not only want to measure how they move on the sky, but we want to also know whether they go towards us or go away, and how fast they want to approach us and go away. This is, as I said, very similar to how the police does it with the radar, or what you know, for example, from the ambulance. If the ambulance approaches you, the sound gets higher in tone. If it goes away, it goes lower in frequency and tone. And the same happens to the light which comes from stars. It's either shifted to higher frequency and lower frequency. And in physics, we call it spectroscopy. You take from the star, you take a spectrum, so different wavelengths at the same time. But now you have to decide yourself with your digital camera. Do you use all the pixels to make an image, or do you put a grating in front of it and put the different wavelengths on different pixels? And to do both at the same time, you have to somehow rearrange the light on the pixels, and this is called integral field spectroscopy. And so you would say the symbols, but actually the most efficient way, and this is also how it's done, for example, on this James Webb Space Telescope now in space, is something which we developed and also around this time, is what we call image slicing. So you have a little stack of mirror, and actually if light comes in, you put one line in a different direction, the next line yet in a different direction, then you have a second set of mirrors, which redirects the light again to what we call a long slit. And then you can be a traditional laboratory physicist who puts a grating behind and make a spectrum for every point in the original image. So we have a data cube where we have the wavelength, or you could say the velocity of the star, and the image of the field. And so these two things now, adaptive optics and 3D integral field spectroscopy, now was setting in around 2000. And so now what we could do is we could zoom in yet by another factor 10 and make sharper images. And now what you see here is a time lapse of observations of the order of 15 years, 16 years. And so we not only see that some of the stars move very fast, as we showed before, but there's one particular star which actually moves around, typically an unknown object, but here you actually see a little bit. It flickers every once in a while. This is the black hole, or emission from the black hole, and the star is falling around. So around 2000-ish, 2003, 2005, there were a few key measurements already known about the black hole. We've seen that a star is falling around something which is typically unseen. You can use Kepler law, and from the Kepler law, you can determine the mass. A few million times the mass of our sun must here be in the middle. The next thing then is this little thing here, actually, in the focus of the ellipse. Every once in a while it shines up. You see this little thing here? It gets bright. This is what we call a flare, and you will see later animation on how we envision what happens there is magnetic fields reconnect like a solar flare, accelerate particles to such a high temperature that you see them at X-ray and also in the infrared light. So we've seen accretion on the dark object of a few million solar masses. And with this technique, integral field spectroscopy, we could measure the velocity of each of the stars along the line of sight. So the situation back then was a pretty strong case for a massive black hole in the center of the Milky Way. And so this is also one of my colleagues, Stefan Gillison, who joined around that time with the the most precise measurements of the orbit and the velocities. This is what you see here. And now the last question was, which we have to sort out, is this object, which is 4 million times the mass of the sun, really small and carries all of that? And this was coming out of the radio wavelengths. So this is a image at radio wavelengths, where you typically see gas, hot gas, or very hot gas, synchrotron radiation. And you see here in the middle, there's a little point source. Actually, this is again a emission from the black hole, very close to the black hole. And so Mark Reed from Harvard University, so he measured the position of this object here over 10 years, and it didn't move, not at all. And so what does it? It's surprising, because you've seen this image of the many stars, and if the star moves like that, you would expect that the other object in the center is a little bit shaken around by the many stars. But since this object was not moving at all, the shaking didn't matter. So which means that it must be so massive, what the mass we've measured here, and the size and the not moving made us sure that this object must be so massive that it's not shaken around by surrounding stars. So the case of the stellar orbit measuring the mass in the radio observation of a very tiny object which is not shaken made this very strong case. So in a way, you could have given, I would say, the Nobel Prize already at this period, 2005 to 2010. There was not much left. We still had not the full proof that this thing in the radio, which is not shaken, is really the mass here. It could have been a radio source, for example, in the background, which is not shaken, for example. So it's not bulletproof, but as I said, it was already a very strong case for having a dark object. And then so the landscape in 2005 was on the observation side. We've seen that sometimes there's emission coming. We had the stars, and we had a theory behind. And the theory behind actually was very exciting to see, because if there's what makes these flares and emission from the black hole is matter which is falling onto the black hole, it will move in a small circle. The size of the circle is maybe that big on the moon, if you would project it on the moon. So if you could build an instrument which can measure on the moon a little motion of that size, you should be able to see whether this thing moves around at almost a substantial fraction of the speed of light around an unseen object. The other thing which if you have that precision, if you take the stars and think of, let's look for stars which are closer in, for example, you would see the effects of Einstein's theory being different than Newton's theory. So in Newton's theory, stars or all orbits or planets are perfect ellipses which close. But around a black hole, actually, ellipses will not close, but they will tick each time with every revolution a little bit. But we would have to measure a few 10 times to 1,000 times better than what we've done before with adaptive optics. But this was now also the time in 2005, actually, when there were good progress on combining telescopes. This is what we call interferometry. Therefore, you can make even sharper images because the telescope is as big as the separation of the telescope was working. So here in Cambridge, a very strong group who demonstrated interferometry on smaller telescopes in the US. And at the same time, technology was evolving very rapidly on telecommunication, single mode fibers, network fibers, components to manipulate the light for telecommunication. So all of that was there. So can we bring that together, the modern technology, the supposedly black hole in the center, the understanding that we will see particular fascinating effects. And so we made predictions, not too difficult to make. You would see gas falling around the black hole in half an hour at a third the speed of light. And we should see faint and fainter stars to reveal the subtleties of this general relativity. And so this is now where we put in this proposal to make a new instrument called gravity at this observatory of the Europeans in Chile. And so what it does, it brings the light together from the telescope. And in the end, we can make images, now use a unit, a few milliarc seconds. I will explain that to you what it means. And all of that with the new technology, we thought we can do it 1,000 times more sensitive than what was possible before. So this was the start of this gravity experiment. And so now let me introduce a little bit the scales we are talking about. So thought experiment. So our telescope sit here in South America. We want to look at a football game, but on the moon. And so we take a stadium, well, this is from Munich, you imagine, and so we put it on the moon, which is also good for some other clubs, and we want to look from here over there. And so even with this adaptive optics and the biggest telescopes, you can barely see the shape of the stadium. But now if you put the telescopes together to a single telescope, actually you can resolve a few meters, so you can see a car, so to say. And if you can even measure the position of a car, we can measure to a few centimeters on the moon. So in a way, we can start see the ball moving around on the moon in a football. And so this is made possible with this interferometry. So now let's do it. And this let's do it was, well, conceptually simple, but in practice it was quite a mess to make it work. And so let's start and follow the light from the black hole, actually what we have to do to the light to see the black hole. And so the first thing is, which was already there, is we need an observatory. So our observatory is called the Parallel Observatory of the European Southern Observatory. So this good dozen of European countries joined together to build a big observatory in the Southern Hemisphere. So this is in Chile, in the Atacama Desert. It's very close to the Pacific. So here in the background, you've already seen the sea, only 20 kilometers maybe away. But the sea is very cold, so all of the clouds stay down on top of the sea. And up at the observatory are in the full desert. So it's amongst the most dry deserts in the world. This is where the Europeans put their telescopes. Initially, we wanted to build a bigger telescope, 20 meters almost in size. But our companies told us we can't. And so they built 4 8-meter telescopes. But we had some very clever guys and ladies who were envisioning this observatory. They put a possibility to bring the light together from the telescope to form this interferometer. And so now bringing the light together is only one thing, but we have to do many more things to superimpose the light from the telescope. You have to control things to a level, a fraction of the wavelength of a light, and the wavelength of a light is a hundredth of the thickness of a hair. So you have to control all the observatory to a very tiny fraction of the thickness of a hair. And so we bring down the light first to the basement, and down in the basement here we have this, what I introduced before, this adaptive optics. So we take part of the light, send it to a special detector, and this is what you will see here, which measures 1,000 times per second this deformation of the wavefront from the turbulence on top of the telescopes. This is a detector which looked like that. Also here, we were lucky right at the time with our development, we could make clearly noiseless detectors for the first time to make this possible at infrared wavelengths. But now when you have prepared the light for a single telescope, we have to do the same for the 4 together. So you bring the light through little tunnels to a central laboratory. And in the central laboratory, we have our instrument. Our instrument is how it looks like. It's in vacuum because it's cooled. We are working at infrared wavelengths, which means we look at thermal light. So we cool everything to the temperature of minus 200 degrees, the detectors. And here we have to prepare the light to bring it together. And prepare this light, what we do is we again take part of the starlight and analyze it with sensors to correct the perturbation of the telescope. And then we send laser beacons up from the instrument to the telescope to adjust everything on this fraction of a wavelength of the light to stabilize things. So lasers going up and down and many control loops. And then the actual interference we do in in this single in fibers. So these are these telecommunication fibers, not really telecommunication. They are from a special material because we infrared astronomers work at different light, but these fibers are good. You can stretch them. So literally, this little actuators where you can stretch them to adjust the path length. You can twist them. This is what you see here, physically twist these fibers, because light actually has a direction where it oscillates. It's called polarization. Also that you have to adjust between the telescope. So if you've done that, all of this massaging of the light from the 4 telescopes arrive to a fraction of the wavelength in this, what we call integrated optics. This is the equivalent of electronics integrated circuit. So we also imprint little wires for us waveguides where we can overlay the light and shift the light a little bit. And in the end, then we make also a spectrum as I introduced before. And this is how the signal looks on the detector. It doesn't tell now much yet, but what you see is you get things bright and faint and bright and faint. And this is what we call interference. If you have, say, on the sea, you have two ships which make waves. And if the waves come together, they interfere and they make a bigger and smaller, so to say, a superposition. And this superposition, which we record at different wavelengths. And so because we have 4 telescopes, we can make 6 superpositions for each pair of a telescope. And here, forget about the numbers and so on, but in the end, for every telescope, what you get interference patterns or wave pattern, bright and faint. And if you measure that often enough during the night, this is what we do for a few hours, then projection changes. And then it's a little bit like at the doctor when he makes a tomography of your X-ray from your head. We also make a kind, not a tomography, but we can put all of these measurements, which are cuts in different directions, make an image. And then it still looks a little bit ugly here, but if you put some massaging to the image, then you get a nice image. And this is a true image. So this is now the black hole, and this is the star when it was closest to the black hole. And so now this brings me to the last building block of this black hole paradigm. So this was adaptive optics, and now come true images out of this interferometry, combining the light from the telescopes. And so we made the experiment such just barely that we were ready when the star was falling around. And so we were at the telescope in 2016. We knew it was coming in 2018. So we were barely in time to be there. And then we could follow that star falling around the black hole. We've seen the black hole now all the time because we are so more sensitive. And we could measure actually the position very precisely, as I said before, to about that size on the moon. And so in a way, this nailed it down. And then not expected anymore. Actually, then our colleagues Reinhard, Andrea, and Roger got the Nobel Prize in 2020 for the discovery, still in the Nobel citation, carefully phrased, for the discovery of a supermassive dark object, because the black hole yet is still some more, as we said. The black hole has this event horizon, a point of no return, and we will have problems. But with interferometry now, it's first come to the great things, not yet to the future. So what we could do is we could make now precision tests, and so we now actually know the mass in the distance to this object to a fraction of a percent, a small fraction. I'm not sure who of you knows your own weight to the fraction of a percent. So we can now even think of more experiments. You can go back to this picture from Einstein. Space-time is curved. Space is curved and time goes at different speeds. So a clock which is closer to a heavy mass or black hole should go slower than a clock which is farther away. So if you put a clock on the star and let it come out from the outside and move inside, the clock should go slower. And we do not have not a direct clock, but we again have this atomic light emission. So when an atom emits light, it comes out at a special wavelength. This is what we measure as a redshift. And so there's effect from what I explained before, the Doppler effect from what you know from the radar. But then on top of that, the clock goes slower. And so the object becomes redder than what you would expect close to it. And this is the physical measurement behind. This is the difference between the Newtonian, where the clock goes at the same speed, and the Einstein's view of a black hole. And this peak here is when the star goes closest to the black hole. And so in 2018, we could publish that. So this was now the detection that time goes slower in a curved space-time around a black hole. Now we come to the other thing. And so this is Karl Schwarzschild. So shortly after Einstein developed his theory in 1910 around, and Schwarzschild, 15, excuse me, Schwarzschild already found solutions for black holes for the space curve time. And there's another effect which makes curved space-time different than Newtonian motion. So we had a time part of space-time, but there's also the space part of space-time. And you can see that, for example, in the orbit of an object in Newtonian or Keplerian theory, you are always on an ellipse. And this will remain the same ellipse. But if you now go to this curved space-time, actually when you go through the closest approach, you will get on a slightly new ellipse. It will rotate. And this is called the Schwarzschild precession. This is a very tiny effect, even for that star and the black hole. So this is why with adaptive optics, one cannot see it. But now with interferometry, so this is an artist's animation, when you get close enough, you get on a new ellipse. And so this is what you see. This is in 2005, when we observed the first time the star. These are now the new measurement in 2020. And so you see we are this highly oversaturated. We are this new part. So we've done also tested the second prediction from Einstein on around black holes. Now we come to this question, this 4 million. So we have now quite a lot. We have an object which is 4 million times the mass of the sun. We have a theory with Penrose and Einstein, which would say if that object is small enough, it must be a black hole or become a black hole. This is what Penrose said. And what we still have to say is that what we see is small enough. This is, or not what we see, that the mass is in a small enough volume. This was this radio picture I was giving you before. But radio might be something different to what we have, but what we now can do in the infrared. You remember this black hole was shining up in a once in a while. So now I reversed the experiment. Within an hour, the star doesn't move much. Then I now measure the separation between the star and the emission from the black hole. And then within 1 hour, this is what happens if the black hole, when the black hole shines up. You see the emission from the black hole makes a little circle. And so in 45 minutes, these are the measurements here. The emission from the black hole is doing a little circle, the size roughly of a solar system, but this is about 30% the speed of light. And so now, if you again calculate from Kepler, so what you find is that this mass of 4 million times the mass of the sun must be within a small region of our solar system roughly. And this is not so much larger than the size of the event horizon. The radius is 5 times the event horizon size where this matter is falling around. So this is now a visualization from a physics modulation and the artist superposition of that. So what we envision that happens there is around the black hole, there is magnetic fields from gas which is flowing in. And in these magnetic fields, these magnetic lines, they make a short, and then there are particles accelerate. You get a hot spot, which is moving around the black hole only a few times the separation of this event horizon. And so this is very similar to this picture which was coming a year later around a different black hole. M87 is the name of another galaxy. This is a black hole which is not only a few million times the mass of the sun, but a few 100 million times the mass of the sun. And so what they could see in the radio, you can make a telescope even bigger and sharper. They've seen an image of the black hole where you again see the emission very close to the size of the event horizon. And so this is what we have observed in the infrared in the center of the galaxy, but in a way differently. This is a static image because the black hole is so massive that things move slowly, while our black hole is smaller, so things, the time scales are shorter. Within half an hour, things move around. In the picture, what we have is like in our sun, magnetic fields are wind up, and at some point, magnetic fields make a short, accelerate the electrons to energies up to that you see them even in the X-rays. We can observe that with the X-ray telescopes, which then also in the infrared show this motion. And so this was a pretty good time, or is a pretty good time with our interferometer. And despite this gravity experiment was actually built to exactly do what I've shown you, to measure the Schwarzschild precession, the redshift, and this flare motion close to the black hole. With this new technology which we are bringing to the telescope, we really could bring it to a revolution in high angular resolution astronomy. This is what this conference is about. We could measure the masses of black holes very far away, 1 billion light years. We could make images. We are so sharp that we can see the exoplanets and actually analyze the atmosphere in the atmosphere of the exoplanets. All of that is possible with this interferometry. So let me acknowledge here that the group who've made this experiment possible. So in total, we maybe were a good 100 people from a handful of institutes in Europe. So there's the European Southern Observatory, which holds the instrument. You see a few of our colleagues there, the former director, which approved it and brought it forward, the current director, and a few colleagues from the observatory to make the project work. Our part of our group at MVE, with Reinhard Genzel and Linda Tacconi. For example, you've seen Stefan Gillison, Oliver Pfuhl, who started as a PhD and now is also at ESO. We have our colleagues in Portugal, in Holland, very strongly our colleagues in Paris who brought the interferometric expertise, Guy Perron from Paris, Sylvestre Lacoeur and Thibaut Pomor, Karine Perrault from Grenoble. And then in Germany, we had 2 more institutes, the Max Planck Institute in Heidelberg and the University in Cologne, to participate in that. So where are we now, 2 years later, 3 years later? The star is now out of the field. It has moved up here on the screen. So now actually we can look for fainter stars because we are not blended anymore by this bright star. And this is what you see here now. So you see the black hole actually is all the time. It's not the faintest object anymore. We now see stars which is 100 times fainter than the star which was making this nice ellipse. We see 3 other stars in here. One of them actually is getting closer to the black hole than this famous star was doing. Other star, this one is on orbit, which has a shorter period that is following around. So in what was a single star with a single telescope now you get a handful of stars. And if we're starting to map around the region to look for ever more of these stars, which you partly because they have names to it, we've known from out there, but when they come in, before we couldn't resolve them anymore, but with interferometry now we can resolve them. We can make this kind of images within what a single telescope could resolve of that size. And so why do we do that? And because something is wrong with, I don't know, but there's reason to believe that Einstein's theory of gravity is not complete. And the reason for that is that if you take this black hole and the mathematics behind it, and what also Penrose has done, is that there will be a singularity in the center of the black hole. The physics breaks down. All quantities get infinity. Normally, you will have a way to deal with that. In electromagnetics, you introduce quantum mechanics, and then you can, we call it normalized infinity in the electric field. But this quantum mechanics actually does not work when you apply it to the equations of Einstein. So we've not found a simple quantization. So the toolbox we know from classical mechanics or from electricity to take a a field which has infinities to mitigate these infinities with a toolbox which we call quantum mechanics. This doesn't work for gravity yet. And then there's also, we make our life easier. This is actually, well, we have hypotheses or conjectures. And so this is coming also from Penrose. We don't mind, you put the singularity always in a horizon that I cannot look behind. So we should not care whether singularity is there or not, because it's never observable. But it's not fully true. In mathematics, you can also find solution where you have the singularity of Einstein's equation without a horizon. So this is a conjecture. It's called cosmic censorship. And then there are other things which are special about black holes, even if you have a deformed matter before. So you take an ellipsoid and let it collapse to a black hole. In the end, the gravitational field outside the black hole will not know anymore about the deformation. And this is called the no-hair theorem. This is coming from Wheeler, another very famous theoretician in general relativity. So, why do I bring these two things? That we always have event horizon, and that the black hole is described by very few numbers. This is what this means, is because it's linked to yet another property of space-time around black hole in Einstein's view, is that the space-time can rotate. So if the original matter was rotating, it's tracking the space-time with it around the black hole. And both of what I showed you before, the existence of event horizon and this no-hair theorem are linked to the spinning space-time. So we want to measure the spin of the black hole in the galactic center. And you can do that in a way. There's simple physics behind. If your rocket goes together with the spinning space-time, you can get a little bit closer. So things get smaller, the redshift gets larger. So in a way, one could easily measure. But the problem is all of these effects also scale with the mass of the black hole. So do we assign it to the spin or to the mass? We don't know. So the way to do the experiment right is to go out of the plane of the spinning space-time, go perpendicular, for example, with a star, which can come from any direction. And then you could actually distinguish the effects. And this is what we are going for in the next 10 years to measure the spin of the black hole, to then test this, what we call the no-hair theorem, ideally. And the way to do that is we are currently upgrading our interferometer with better adaptive optics for all of the telescopes. So far, we only have a laser on one of the telescopes, and now upgrading the full observatory with better adaptive optics with laser for all of them. We are building a very big telescope, only 30 kilometers on the next mountain in Chile, which is called the extremely large telescope, which will be 40 meters, not as big as the interferometer, so not as sharp, but with a big collecting area to measure the spectra in the radial velocity. So here the sharpness, here the light bucket for the spectroscopy. And then we can again do this event horizon telescope observations. One can observe radio telescope across the world and make images also of the center of the galactic center. They are not out yet, and the reason is what I described before. So we have an image of a black hole which is far away and much more massive, and therefore things are smaller. In the galactic center, actually things move very quickly, and radio interferometrists also have to sample the image while the Earth rotates. Their measurements scan the image, so to say, and if things changes in 30 minutes, which does, it makes the life so much easier. And this is why the image of the black hole in the galactic center is not yet published, observed, but not yet published. And with that, so now with our interferometer here, when we make everything yet in fact 100 better, this is roughly what we want to do. And there are quite other things we want to touch. Well, we are pretty sure we will get to exoplanets which are not accessible with any other technique. We will find, and we will be able to probe the atmosphere of this exoplanets. We are so more sensitive than to also look on black holes in a very distant universe. At some time, they must have formed roughly at 10 billion years ago. And it's still a big puzzle how these black holes, some of them have a billion times the mass of the sun, can have formed so quickly in the universe. So this is what we will address and things like that. And with that, I would like to thank you very much for your patience. And I hope you could enjoy a bit.
Yes, thank you. Thank you very much. Really a powerful reminder how important technology is for the progress of astronomy nowadays. Are there any questions? Maybe let me start with one. Oh, please, yes.
Whether there was any tie-up between gravity wave measurements with this optical work.
Can you say it again, please?
Was there any tie-up with the work of gravitational waves with this optical work?
No, not yet. Not yet. It may be also some time to go. So the gravitational waves are also detected by interferometry, but differently. So what they do is they take a laser, send it in two directions, and then measure the distance or compare the distance to the two light paths. And what they've done so far is they made these interferometers on Earth, which is a pretty shaky ground. So they can actually observe best things which happen very fast. That means these are small black holes. These are two stellar, we call them stellar black holes. They have a mass of typically 3 solar masses. And when they merge in the final stage, then they make a sweep, which is well in this range where the noise is little. For example, our black hole is 1 million times more massive. So if a star would fall in, this would make not whoop, but it would be every half an hour you would get a stretch. And half an hour is not a good time scale because you have your subway going around, you have your little earthquakes all across the world. So they cannot measure these low frequencies. So they measure high frequencies, which means small black holes. And this is the reason why they want to go to space. So the next big project in gravitational wave is they want to put the interferometer in space because there's no shaking subway nearby. And so they can measure these very low frequencies. And then it doesn't go so fast, but they can give themselves a few days to look very precisely on something which then falls in. And this is then where we might have overlap. Well, these are always events which are only a single time. It's difficult. We will have to see where this comes together. Another thing where there is an overlap is that these gravitational waves, now they see black holes. So black holes can also be a few solar masses. At the end, when a star explodes, it can shrink to a black hole. But it should not be too heavy from all what we understand, only a few times the mass of the sun. But these gravitational waves now have found black holes which are too heavy for what we understand of stellar evolution. So even the small black holes must become larger. We don't know whether this is coming from merging or whether they are formed so heavy. And we will, with gravity, we might be able to find some of these progenitors. So this is in a way this overlap with the gravitational waves. Gravitational waves find massive stellar black holes, which we otherwise have not seen. And there's a technique where we could contribute. It is something like that. If the stellar black holes go in front of a star in the background, the light from the star in the background will make a little ring. This is called a microlens. And the size of that thing is too small for a telescope. This is again very much like this is how you could see it with interferometry. Without interferometry, you cannot resolve it. And so now in interferometry, there were already 3 of these things imaged, resolved. And then if you can measure again the diameter, you know how heavy this is. So far, the things which have been seen were all normal objects in the middle, but with this upgrade of our interferometer, we now should be able to observe many more of these events, and then maybe we find those which are building this gravitational waves then later in a way.
So another question.
Hi, what do we know about the stars that are orbiting the black hole?
Well, we know quite a number of things. So number one is the ones which we see are very bright, quite massive, about 10 to 20 times to 40 times the mass of our sun, and therefore must be very young. So the lifetime of a star is linked how massive it is. If you have a very massive star, it burns like crazy. It evaporates its energy very quickly. So the fact that we see these massive young stars is actually puzzling, because we do not know how the stars come to so close to the black hole. In a way, you could have two scenarios. The one is they have formed there, but this doesn't work well. To form a star, you need to start with a gas cloud and then shrink it. But actually here the gravitational forces are so big, the tidal forces, that you cannot have a gas cloud collapse. So they cannot have formed there. So now the question is, how did these stars come so close? And our best model for that is like that. So you have still at a light year away, so outside our field, you have gas streams coming in, which circularize, and you have a disk of gas which forms stars within. It's still at light year scale, not yet at, so we still have to bring them in by a factor 100. And so our thinking is that we have outside perturbation, which brings some of the stars in. And again, some or many of the stars actually live in binary systems, so two stars together. And then when you come close to the black hole, you catch the more heavy star and you eject the lower mass star. This is called the Hill's mechanism. And so this hierarchy of, we call it relaxation mechanism, is the one which we foresee, or which we envision, which brings the star close in. But again, this is a reason why we want to see ever more of the stars, because you can test this hypothesis if the ellipse which will remain will be an echo from the ellipse which the binary star had before initially. And so actually you can learn a lot. The more of the stars you find, we will finally come to the answer to this question. But for the moment, it's this what I say, first farther out, then a scattering in, and then this Hill's mechanism which ejects one of the companions and leaves the massive star in the center.
Have we detected any of these stars that have been ejected, traveling at very high speeds?
Under debate. So these stars are called hypervelocity stars. Indeed, if you look on the full sky, you find a good handful. I don't know, I'm not really expert, but a good number of stars which move at velocity so high that they cannot bound to our galaxy. So if you let them continue, they would fly out of our galaxy. Now the question is, what mechanism can make a star move so fast that it can escape? Here you have one, the black hole. So our colleagues are now tracing the stars and looking if and how many of those point back to the center. There is one very good candidate, a few more. The answer is not yet given because the stars not move necessarily in a straight line, because there's a gravitational field, and so it's under debate, but there are these hypervelocity stars which exist and could come from the galactic center. But we see them a few hundred or million years later. They are outside, so we see them in the outer parts of the Milky Way.
Could we detect a stellar mass black hole colliding with our supermassive black hole?
Well, in gravitational waves, if we would have it, yes. With the current technology, I don't know. I don't know. Not the signatures would not be obvious. I would say it can well be an outburst of light, because the black hole, which will go towards the black hole, will certainly perturb a lot this accretion. So the black hole is not naked. You see the black hole sits there, and there's gas streaming, and there's a lot of gas around from stellar winds, which is slowly going towards the black hole. Around the black hole, there is a accretion disk where the gas settles, and then some of the gas is carried to the black hole. And this gas disk normally for a normal black hole is actually very bright. This was this image I showed you in the very beginning. The star, a billion light years away, is a black hole. Gas streams in, circularizes, gets very hot, and shines very strong. The black hole in the galactic center is very special, that there's very little gas nearby currently. There's a lot around from the stars, but very close to the black hole, there's very little, million times less than typically we would say for black holes. And so I could well imagine if now a stellar black hole comes in, it will mix this gas up, and actually it will lead to a perturbation which can then lead to a situation that the gas comes, much more gas comes to the disk, and it will shine up. But I'm incompetent, and I'm giving you a naive picture, my naive picture.
I will then read out a question from the online audience by Joseph Varga. Could gravity detect? Okay, so let's yes, please.
If
Please go ahead.
the laser guide is shining off the atmosphere, will it not perturb slightly differently to the actual starlight? And does the optics need to account for that?
Can you?
So if
the
the laser shines off the atmosphere rather than comes all the way through, does the optics need to account for that? Is it not slightly different?
You are right. So we have a problem with that. So indeed, this artificial laser guide star is a height of 100 kilometers. And when you look on it, you see a cone of the atmosphere, while the starlight is at infinity, and it goes through as a cylinder. So there's a part of the atmosphere which is not seen when you look at the laser. And we overcome that not with that instrument, but with another instrument at the observatory. You shoot several lasers at the same time. Then you look in different directions through the atmosphere. And then you can apply tomographic solutions like X-ray in your head. So you look through the atmosphere in different directions, and then you can reconstruct the full turbulence profile and apply it. Was this the question you were? Mm-hmm. No, it's working decently well, and it's getting better every day.
One question from the online audience. Then afterwards, I'm happy to take your question. Joseph asks, could gravity detect intermediate mass black holes assumed to be hiding in globular clusters?
Yes, so this is one of our science cases. The problem in this, so globular clusters are star clusters which have roughly 1 million suns in them. And they are also supposed that there's maybe black holes which are smaller, maybe a few thousand times the sun of the mass of our sun. Now the problem is, for us is actually, we are very slow in measuring. We need 2 objects and need to see how they move relative to each other. But in these globular clusters, actually it's not so obvious what is the center of the cluster, where to look for. So what you can do is you look for, again, for the motion of the star and see whether there is a region where the stars move particularly fast on average, statistically. And then we can do our measurement between a random combination of stars in this region. It will be a very costly experiment because we would not know which exactly. And globular clusters, the stars are also comparably faint and still comparably large separated for us. So it's also technically difficult, but we are working on it. But we have not started with that program because it's so costly to observe. But we could, and it's
From some
part of
masses to
what we want to
millions of masses. In the audience, yes, please.
When you mentioned that they were kind of like using laser guide stars isn't perfect, does that mean there's a use for James Webb in observing the galactic center, or is the sheer size of the array you have in South America mean that there's no real point?
I think for the galactic center, but time will tell us. The James Webb, for our standards, is a comparably small telescope. So it has a diameter of 6.5 meters. I think it will be diffraction limit, so it will be very sharp. That is true. But compared to that image, what we have, so for the James Webb telescope, let me go. So the sharpness of the James Webb telescope will be about that. This will be the size of a star from the James Webb telescope. So you now then can apply techniques which we call deconvolution. If you just have enough signal to noise, we call it enough photons, you can try to disentangle it. So in a way, you can be sharper than the diffraction limit. I would say it's a matter of how many photons you have and how complex your field is. But it will be very limited. It also has, for that kind of science, for the stellar velocities, this is another case. If you can measure the radial velocity from the spectra very precisely, you can also find subtle relativistic effects. Also here, the James Webb telescope has only comparably low spectral resolution of a few, I don't know, 100 kilometers per second of that order. And so here on Earth, our instruments can measure much more precisely the velocity of the stars, and the angular resolution is really 30 times better. So I would say it's not a galactic center black hole machine, clearly not. It's a black hole in the early universe machine.
I have another question from the online audience. Colin asks, you haven't mentioned dark matter. Does this affect the orbits of the stars orbiting the galactic black hole?
We say no. So what we can measure is by precisely measuring the shape of this ellipse. You can not only measure this Schwarzschild precession, but if there is an extended dark matter, one would have a counteracting effect. If you put additional mass and distribute it, the ellipse actually will also not close, but move in the other direction. And so from our measurements, what we can do is we can give an upper limit of an extended mass, could be a dark matter, which is of the order 1,000-ish solar masses. And so this is negligible to the mass of the black hole. And so probably not in substantial amount dark matter. We have also not seen other indications. Dark matter, what is looking for it, obviously dark matter is one of the most important topics in astronomy. Dark matter, depending on the part, what kind of particles it is, they could also annihilate, so they could destroy themselves with antiparticles. And so indeed, one is looking for emission from the galactic center region, whether there's a pile up of unseen particles. For the moment, we do not have any evidence. The contrary, we would say we have very strong upper limits for the amount of dark matter which could be there.
Mm-hmm. You also mentioned that the Nobel Committee and maybe also some astronomers hesitated with really embracing it as an absolute certainty that it is a black hole. So what have been, or what are the alternative ideas that people have that could have such a mass but not be a black hole?
Well, there are alternatives in a way. If you have particles which, so to say, can condense on something which is slightly larger, fermions, for example, a fermion ball, if you have particles which are heavy enough. Fermions, like electrons, you cannot bunch electrons too close to each other. There is in quantum mechanics a a principle, for example, that says two electrons cannot be in the same state. That means also not too close to each other. So in a way, depending on how heavy these particles are, you could construct something which is just a little bit larger than a black hole, which has event horizon, or you could take different particles like boson, which you can get closer to each other, and could still make like that. They all have to be tuned very, very finely to still be consistent with the observations. They would have to be very compact. They would not have a surface where the matter can collide on. Well, you see, we actually know much more. So from the radio observation, for example, you see how much matter is there. We know the density of the gas, we know the accretion rate, we know how much the magnetic field is, the light is changed in propagation. If I take all of that together, you have to very fine-tune the alternatives. And so you see what we had. We know the mass. We know it's within from the flare, we know it's within a 5 to 10 gravitational radius. It's very difficult to construct a model where you have extended mass, which is not a black hole, and which remains not a black hole for a long enough time. Because you see, if you have a mass, even if it's not normal matter, it will accrete normal matter. And the normal matter, say the gas from the stars, will collapse towards a black hole. And if you have a black hole, it will also get everything else with it. So you not only need to explain, make it fine-tuned to what we see, but in a way you also have to make it fine-tuned that for 1 billion years it need to remain stable at something which is just a little bit bigger than a black hole would be. So there are alternatives, fine-tuned and fine-tuned both in spatial extent, in mass, but also in lifetime.
So even further work to do to rule out this very last.
We are getting closer and closer. I think now we are at 5 Schwarzschild radii. Then we get an image, then we are at 3 Schwarzschild radii. So you see, there's very little room to remain with really fundamentally different solutions to what we see.
Is there another question from the audience? Check online. Oh yes, there's an online question. Jan asks, would the presence in the sky of thousands of satellites relaying the internet in the coming years to be critical to the observing problem?
Not to us, because our field of view is so tiny, so we never see a satellite passing through by accident. For astronomy as such, it's a big problem because we have a lot of observatory, especially now, surveying the whole sky every night de facto, because the sky is not static. It's an old-fashioned picture. You see here things are moving, but actually we have a lot of transiting events. And so there's a full machinery now which looks at the sky every day. And here all of the satellites are a real problem because you see them everywhere.
Mm-hmm. I remember with some instruments that you built with this adaptive optic techniques. So it was about 10 years ago, giant gas clouds are moving towards a galactic center. Is there any news on that? Can you still trace that gas cloud?
So we are just putting again, well, this is more for the experts. So this first instrument, which I presented here with integral field spectroscopy, we demounted 2 years ago to upgrade it. We just brought it back this year. And this is this instrument which makes images and spectra at the same time. So later this year, I'm pretty sure we will again see this cloud. So there's a gas cloud maybe falling at this distance around the black hole. It was discovered around, now beat me, 2012 or something like that. So what we see is a gas of cloud. You don't see the emission from a star, but you see only the emission from atomic gas. And what we see is, so this is a little cloud of gas, which is falling around the black hole, very similar to the orbit which you have seen for the star, which is, while it's passing by, is stretched gravitational, and if it then falls by, is coming together again. It's clear that it's a gas of cloud. We do not know whether this gas of cloud has an object in the center which generates the gas. So the origin of this gas is unknown. At that time, and still very plausible scenarios, that it's winds from nearby stars around. There's a lot of wind from stars, and when wind collides of stars, you actually create these clouds, and the orbit would match that. But there are also other scenarios where you could have a young star in there which spills out the gas, or you have a star in formation with a disk, with a gas disk. The star, the object is not seen in the center, but there's still the question where the gas is coming from. So I'm pretty sure we will see it as soon as we point air respect to the galactic center. I'm also pretty sure it's still there, and it will have moved around.
Is there another question? If not, then let's thank Dr. Eisenhauer again for visiting us. Great to have you here. Thank you all for coming, and I wish you a good evening.
Thank you very much for your interest.